Yes. So last time we were talking about this polarization ellipse, and you can actually choose any general axes like this x and y, uh, this x and y, uh, and you can measure the electric field amplitude and the phases for the for the amplitude along the x direction and along the y direction. But even better way to represent this polarization is not to worry about individual phases phi 1 and phi 2, but just the relative phase between these two components. If you do that, you can actually describe it in terms of this polarization ellipse. Okay. So this Ex, Ey were general amplitudes along any general x and y axes, and Ex prime and Ey prime were the amplitudes along the principal axes. Okay, with their with their amplitudes epsilon naught cos beta and minus epsilon naught sine beta. This minus sign is more of a convention. Okay. Uh,
Sir, can you, I mean, what is this, that determinant M you have written? What is the physical significance of this? And I mean,
this
this
one.
ellipse, this EX2, I mean, this EX, EY, and then 1 by epsilon 1 square minus, yeah,
Yes.
below that, yes,
This matrix, right? So if
yes,
you this equation, so this is an equation for a conic section, right? We know that this is ax squared plus by squared plus uh, xy. So cxy equals a constant, right? So if you can write this equation for conic section as in a matrix form. So you have ex, ey, a row vector, a matrix, and a column vector. So from the properties of conic sections, you can actually say that if this coefficient matrix has a determinant which is greater than 0, it's an ellipse. In other words, if it is a if you make a matrix for this one, x square by a square plus y square by b square equal to 1, what is the matrix for this one? It's just 1 by uh, just a sec.
1 by A square and 1 by B square.
1 by a square, 0, 0, 1 by b square, right?
Yes.
So basically the determinant of this is greater than 0. So this is just for sort of showing you, motivating why this greater than 0 always gives you an ellipse. And you know that, for matrices, you can, you have similar matrices, you can actually, as long as the eigenvalues of a matrix are the same, the uh, the properties of the matrices are the same. They are the matrices with the same eigenvalues but different sort of coefficients, right, are equivalent. They're called similar matrices, right? So you can transform one matrix to another by sort of doing something called a similarity transform. So the point is, if, like, for example, for this one, you can always transform this matrix, right, into a form which is a diagonal form, right? And this form has a determinant which is greater than 0. So in general, this is the condition. If you have a conic section equation which is written in this form, xy, a matrix xy, row and row and column matrix, then this is greater than 0. This is an ellipse, right? You can actually, there are various ways of saying the same thing. Okay, but the point is actually this, right? So basically, it's this electric field does not map out, for example, a hyperbola or a parabola, right? That's also possible if you have a general form x squared, ax squared plus by squared equals to c squared, right? But this is an ellipse. That's the point of this. Okay. So by just comparing these various coefficients, we were able to relate. We were able to relate. We were able to relate this. amplitudes measured in the lab frame, like XY coordinates, and the amplitude measured in the principal axes, right? It was epsilon naught cos beta, right? The amplitudes along the semi-major and semi-minor axes were this cos beta, sin beta. And in fact, beta is absolute value of beta is less than 45 degrees because we are assuming that epsilon 1 is the semi-major axis, right? So epsilon naught cos beta is bigger in the magnitude than epsilon naught sin beta. Okay, this is IQUV. So these are called Stokes parameters: intensity, Q parameter, U, and V parameter. V, yeah, and if we introduce these parameters, they are actually related to the electric field amplitudes in this way. Okay, and by comparing these coefficients, we can relate the general epsilon 1, epsilon 2, phi 1, and phi 2 to the principal parameters epsilon naught, beta, and chi. So there are only three independent parameters which characterize these monochromatic plane waves. Okay, and these are epsilon naught, beta, and chi, and they're most conveniently written in terms of these Stokes parameters, which of course can always be obtained by making measurements in any frame that you want, any XY axis that you choose. You can measure epsilon 1, epsilon 2, the amplitudes in some, in a set of orthogonal coordinates, and you can measure this, you can measure the phases and so on. In fact, you can measure all these experimentally, okay, easily. So once you know epsilon 1, epsilon 2, phi 1, phi 2, or not even phi 1, phi 2, the difference between the two phases, you get these principal parameters, epsilon naught, beta, and chi. Epsilon naught is the overall amplitude of the electromagnetic waves. Beta is this beta defines this ratio of this is beta, right? This is epsilon naught cos beta. This is epsilon naught absolute value of sin beta. So this beta parameters determines the eccentricity of this ellipse, or the ratio of the semi-major and the semi-minor axes. So that's beta, and the chi is just the orientation relative to the x-axis of this principal axis. Okay. And these are the formula, this and this, in terms of the Stokes parameters. And this is the relation between I, Q, U, and V for a monochromatic light. Monochromatic means a single frequency omega, right? In principle, you can have, if omega is a solution, some other frequency is also solution. But here we are only talking about a fixed frequency or the variation of the wave. Okay. And then from these relations here, you can actually make a sphere that can represent these different Stokes parameters I, Q, U, and V. So if we choose V as the z-axis of your spherical coordinate, this is sort of like spherical coordinate system. So z-axis, V can be identified as z-axis, U with y-axis, and Q with x-axis. So Q, U, V. So this is a Q, U, V plane, and from the normalization condition, we know that Q square plus U square plus V square equals I square. So that's like so I is like your radius, radial coordinate in spherical coordinates. And this 2 beta is like your latitude, right? Normally in spherical coordinates, we measure the angle theta from the z-axis, but you might as well measure it from the xy plane. They are sort of equivalent. So this is 2 beta. You can actually see V is equal to I. So epsilon naught square is nothing but I sine 2 beta. Right, so this is I sine 2 beta V value. Similarly, Q value is I cos 2 beta cos 2 chi. Right, and similarly U is I cos 2 beta sine 2 chi. So this is called Poincare sphere. Right, so V equal to 0, right? If your Stokes parameter V is 0, this is linear polarization. So V therefore is also called circularity parameter, right? So if V is equal to 0, that means your I lies in this QU plane, and V equal to 0 means that beta, right? Beta is 0, right? If you recall, sine beta was the value of the semi minor axis. So sine 0 is 0. So basically the ellipse becomes a line in this case when beta is 0. So that's why V equal to 0 is linear polarization. V greater than 0 means 2 beta is between 0 and pi by 2, or beta is between 0 and pi by 4. If beta is between 0 and pi by 4, let's go back to the ellipse. If right, so and here, right, so so epsilon 1 prime is equal to epsilon naught cos beta, epsilon 2 prime equals minus epsilon naught sine beta. So if beta is between 0 and pi by 4, this is negative, right? So that means that so if you're starting from here, and if you're sort of increasing the time, the y prime component actually becomes negative if you're starting from here, and it becomes negative and goes in this direction. So this is a clockwise sense of rotation, so which corresponds to the right circular polarization or right elliptical polarization. So so V greater than 0 or beta between 0 by 4 is right elliptical polarization, and V less than 0 is L polarization, elliptical polarization. So that's about, in general it's elliptical polarization. Right. Q by U just determines your chi, right? You can actually see Q by U gives you, U by Q gives you tan 2 chi. So that's just the orientation of the polarization ellipse. Q and U both equal to 0 gives you circular polarization. So what would be the condition for circular polarization? It would be epsilon 1 is equal to epsilon 2 prime, right? So this for circular polarization, basically the semi-major and semi-minor axis should be equal, right? In that case, if this and this are equal, beta should be pi by 4 and 2 beta should be pi by 2. So basically they correspond to these poles. So poles meaning Q and U both are 0. That's circular polarization. And if you're in the upper half plane, it's right polarization, and lower half plane is left polarization. Okay, so good. So this, I had to hurry up on this portion last time. So is there any question on this? Okay, so this is actually simple but very, very useful. So a lot of radio astronomy, for example, is done in these I, Q, U, and V. People deal with these parameters. So it's useful to know these a little bit. So in the later on, if you do research, you may find it a little useful. Okay, so now we'll start with the next topic, which is slightly beyond this monochromatic light that we dealt with. So we are now talking about quasi-monochromatic quasi-monochromatic plane waves. I mean, I should really not call it plane because it has a little different connotation in the sense that for linear polarization, sometimes we use plane polarization, plane polarized light. So, but this is the quasi-monochromatic waves. So, what are quasi-monochromatic waves? I mean, let me so let me actually write down what I mean. So E1 is equal to epsilon 1 t e to the I phi 1 t. Okay. Now, so if you recall, E1 was the x component of the electric field, time varying x component of the electric field, and E2, like in not the quasi but perfectly monochromatic waves, this was, I mean, they had the same form except that this epsilon 1 was a constant and epsilon 2 was the constant, and all the time dependence was actually e to the minus I omega t, right? Now we allow for general time dependence, and so this is the amplitude of the wave and this is the phase of the wave. So we allow amplitude and phase to vary in time. Okay, so this is, and quasi-monochromatic means that, right, so you recall phi 1 was actually equal to minus omega t plus phi 1 naught, some constant phase. So this is how it varied for perfectly monochromatic waves. Okay. But here we allow a slow time dependence on the amplitude and the phase. So there is a slow time dependence. Basically, this factor and this phase factor vary slowly in time. Okay. Now, what does it mean? So previously in the last class, I was actually telling you about that there is no monochromatic wave. There is no real monochromatic wave, right? All waves are actually wave packets. They start with zero amplitude, finish with zero amplitude. So, you have this sort of an envelope, which is called modulation, and you have fast variation. So, typically this variation is very, very fast. So this corresponds to like 2 pi by omega naught, this time period. So this is in time, right? And there is like a width of this envelope, which is like delta t, right? So in the frequency space, so this is sort of like a if omega naught delta t is much bigger than 1, this is quasi-monochromatic. Basically what it means is that the envelope varies much more slowly compared to the the wave itself. Quasi-monochromatic. Okay, and this is the time representation, and we actually did this Fourier transform, and this is like the Fourier. This is schematic only. So this is the most power is actually at omega naught. So this is like E omega square, like power spectrum as a function of omega, and this has like a delta omega, a bandwidth. Okay, and this bandwidth is of order 1 by delta t. Okay, so if delta t is very, very long, so if you have infinitely long wave with the same frequency, then delta omega is 0. Basically it's a delta function, right? So in the same way, so when we are saying we have quasi monochromatic waves, what is happening is that we have a very slow variation of the amplitude and this phase. So it's essentially locally very similar. For many cycles, it looks like a monochromatic wave, right? So this time delta t, over which the phase and amplitude change significantly, is called a coherence time, right? Over this coherence time, the phase difference can sort of vary significantly. So the wave can become, I mean, if you interfere waves after this time, they are no longer coherent. So intensity adds instead of amplitudes, right? Okay. So monochromaticity breaks over a time period greater than the coherence time, basically, because if you are looking at the wave here and here, their frequency will appear very different, right? Because you are in a different part, they don't have a constant amplitude, and also this phase can vary. Okay. Right, and see the optical frequencies, so optical waves, for example, vary very quickly, like 10 to the 14 cycles per second. So typically instruments measure intensity rather than the electric field itself. Like in radio and in microwave, where you have centimeter or meter wavelength, you can actually measure the amplitude and the phase. But in optical, for example, we are generally measuring the intensities. Okay, so intensities in the sense that something like this, right? So for example, this one is the intensity, or in fact proportional to intensity, right? So this bracket represents averaging over 2 pi by omega naught, several of these. So averaging over several of these fast variations, you can get a sense of the amplitude of the wave, right? So this is the intensity. This is actually an absolute value square, because if we are treating this as a complex number, we have to put this. Okay. Now it turns out that although we dealt with Stokes parameters for perfectly monochromatic waves, if you have quasi-monochromatic waves or waves with these slowly varying amplitudes and phases, you can generalize these Stokes parameters. Okay. Okay, so that's good. So let's see. So let's actually consider, say, E1 and E2. So these are your, say, X and Y components of electric field measured by you, and this is some sort of an optical system, like a quarter wave plate, polarizer, or something, or polarizer or whatever. And if you are sort of giving these electric field in the X and Y direction, it produces something E1 prime and E2 prime, right, along X and Y direction. You can also think of this black box as a transformation from lab coordinates to principal axes, right? If you recall, in the polarization ellipse formulation, we could write the principal axes electric fields as a linear combination of these two, right? The amplitude measured along X and Y. Similarly, this one. So we can actually talk about a linear. So it can either represent that transformation, or represent Ex and Ey after the wave. For example, it passes through a quarter wave plate or a polarizer or an attenuator or whatever. So this can also be a general optical system. Okay, the point is E1 prime, E2 prime, these are the transformed electric fields. However you transform, either you make this principal axis transformation, or put some optical system and change the values of E1 prime and E2 prime. So this is equal to, in general, if this is a linear operation, you can write this as this general linear transformation. Okay. So this is a matrix equation, and all these are complex. E1, E2, lambda 1, 1, lambda 1, 2, all these are complex numbers. Okay, and this is a general linear transformation. Let's see. So what is it? So do you guys know about polarizer and a quarter wave plate and a half wave plate, things like those? Hello.
Yes, sir.
Yes, sir.
So, for example, if you have a quarter wave plate, it introduces a phase difference corresponding to a quarter of a wavelength between the two polarizations. So if you have a linearly polarized light which is incident, right? So linearly polarized light meaning E2 is 0 and E1 is non-zero, for example. Then what it will do is the quarter wave plate will convert a linearly polarized light into a circularly polarized light by introducing a phase of pi by 2. Similarly, polarizer will only produce electric field along a certain axis. So all these are linear operations. Okay, good. So then everyone has taken some basic optics course. Okay, so what is the intensity measured at the output here? Okay, so let's talk about that. Right, so the intensity measured at the output would be right. So the intensity measured at the output would be right, E1 prime squared. So basically we have to take a real part of this, right, plus real part of, and then do a square, right? Real part of E2 prime, and then do a square, and then we have to time average it over this fast variation, right? This is what the intensity would be. Okay, right, so let's actually look at so real part of, actually I can also write this as or epsilon 1 prime t is equal to epsilon 1 prime. There is a time dependence here, but the fast time dependence, I write it as this, right? I mean, I can absorb the fast variation here, and I say that this, which includes both the phase and the amplitude, slowly varying phase and amplitude, slowly varying. And phase here. So when I'm averaging with these triangular brackets, I'm actually averaging terms which are varying fast like this. Okay, so right, so what is real part of this? This is something like, this would be like something like E1 prime 0 cos omega t minus phi. right? This would be, when we take final form, this can actually be written like this. Okay, and when we put this square bracket, this will give you a half, right? As I said, so this will be E10 prime square by 2. Here E10 now is a real number. So if we write this, this is nothing but 2 times, right? So when we do this averaging, let me just write, so 2 times real part of E1 prime e to the minus I omega t squared plus similar term in the second direction. Right, so let's see. Right, so basically, this will just give me E squared. So E10 squared plus E20 squared. That's why I need this 2. Okay. Right, so let's see. So everyone knows complex numbers, right? It's a little bit of manipulation of complex numbers. So if we do that, what do we get? So let me just write down 2 times real part of E1 prime e to the minus I omega 2 omega t squared, and this is averaging over the fast variation. Okay, so what is this? What is real part of even prime e to the minus I omega t? So let's just call this z, a complex number. So that's just z plus z star by 2. That's the real part of this, right? So this is, and then we have to take a square, and we have to do 2 times and do this. So this is nothing but 1 by 2 z squared plus z star squared plus twice z star. Okay. Right. So, and recall that z is nothing but this whole complex number. So z is equal to lambda 1 1. So I'm actually using this lambda 1 1 e1 plus lambda 1 2 e2, and in general lambda and e both are complex, and there is an e to the minus I omega t. So this is my z. What is z squared? So z squared is equal to lambda 1 1 squared e1 squared plus lambda 1 2 squared e2 squared plus twice lambda 1 lambda 2 e1 e2. So I'm just squaring it. Sorry, lambda 1 1 lambda 1 2 lambda 1 1 lambda 1 2 e1 e2 e to the minus twice I omega t. Okay, now we put the if we do that, you see that this is the only time dependence, right? and this is fast, this is fast time variation on the time scale of omega. So this averages to 0, right? Because this is like cos 2 omega t. If you average cos 2 omega t over several periods, it averages to 0. Similarly, z star square would average to 0. Okay. So this and this would average to 0. You will just need, sorry, this is not 2z star, it's z, right? So right, so yeah, I think this is fine. So z star, what is z star? This is equal to, now if you take a star of this e to the minus I omega t and e to the plus I omega t will cancel. So this is lambda 1 e1 plus lambda e2 times lambda 1 1 star e1 star. It's just little tedious maths. Right, and then we have this. Here the time dependence has dropped out, so these terms will survive. So this is nothing but so lambda 1 1 lambda 1 1 star. So lambda 1 1 absolute value square e1 absolute value squared plus lambda 1 2 absolute value squared e2 plus lambda 1 1 lambda 1 2 star. And so this is what we'll have. Right, so here, so now here the time the fast time variation was not there, so this is what it will be. There is still some time dependence because the amplitude itself is slowly varying with time, right? But for time scales much less than delta t, this can still be treated as monochromatic. That's why it's quasi-monochromatic. So for example, what does this mean? E1, E2 star. What does this mean? This actually means something like E1T. Okay, and where T is much less than delta T, but much greater than 2 pi by omega. So there is a time scale which is much longer than the fast variation, but smaller than the coherence time. So this averaging is done for that time period. So similarly, we can write, energy measured in the E2 part and so on. So the point is that the power measurement will involve terms like EI, EJ star, right? Where I and J can be 1 or 2, right? So for example, E1, E2 star or E1 absolute value star, which is E1, E1 star, right? Right. So right. So now we can actually write the Stokes parameters of monochromatic waves again. So I, if you recall, was equal to, right? This is nothing but E1, E1, sorry, E1 star plus E2 star. This is the Stokes I for this quasi-monochromatic wave, right? The main difference here is just these triangular brackets appear, right? So that so this would be, and here also triangular brackets, because these amplitudes are slowly varying in time. Okay, what about Q? Q was equal to epsilon1 squared minus epsilon2 squared, right? The difference between the two powers in the principal axes, and that is nothing but E1 star. And recall these I, Q, U, and V are real numbers. So even though E1, E2 are complex, they are arranged such that the result is complex, right? Basically, I star is equal to I. You can actually show it. This is E2 star. So this is Q, U, which was 2 E1 E2 cos phi1 minus phi2. Here again, phi1 and phi2 are slowly varying in time. So this is nothing but this can actually be written as E1 E2 star plus E2 E1 star, right? So so recall this phi1 minus phi2 was the phase difference between E1 and E2. So basically E1 is some amplitude which is slowly varying, e to the I minus I omega t plus I phi1, and E2 was some amplitude which is slowly varying, e to the minus I omega t plus I phi2. Right, so you can actually see that right, you can actually prove it from this, that twice epsilon1 epsilon2 cos phi1 minus phi2 can be written as this, just from the complex numbers. So when you do E1 E2 star, when you do E1 E2 star, you will get this e to the I phi1 minus phi2, right? And the second one will be the complex conjugate. So basically so if you have a number A is equal to A naught, so which is a real, or absolute value of A times cos I phi plus cos phi, just a sec, cos phi plus I sin phi, right? So this is A, and B, let me call it phi A, and B is equal to absolute value of B, which is a real number, cos phi B plus I sin phi B, right? So epsilon1 epsilon2 cos phi1 minus phi2 can actually be written as, I mean, if I want to take A times B star, then you will have terms like cos phi1 minus phi2. Anyway, so let me just write down V. Let me just write down these results. You can actually verify these just by simple complex number manipulation. So this is 2 epsilon1 epsilon2 sine phi1 minus phi2. This is equal to 1 by I okay. So these are actually just written in terms of the complex representation of the field. So if you know the complex representation of the x and y component, you can actually easily get I, Q, U, and V. Previously we had written this, and we had actually written this in terms of these polarization, the principal ellipse representation. So this was like epsilon 0 squared, and this was like the difference between the semi-major and semi-minor axes, and U and V were related to the orientation of the polarization ellipse relative to the x and y. Right, so the mathematics wise and appearance wise, they appear exactly like what we did previously, except this appearance of brackets, and these brackets just represent time averaging, because your instrument is measuring time averaged intensities rather than the amplitude and the phases. Okay. Right, so this reduces to the standard Stokes if we set these to be constant, phi1, phi2, epsilon 1, epsilon 2 be constant. So Stokes parameters are the most general and complete description of radiation intensity, right? So if two lights have the same Stokes parameters, they are indistinguishable by the instruments that you're using. Right, so this means that if your frequency is very, very fast, so whether you have frequency omega or 2 omega, your measurement instrument cannot actually distinguish between it if it is averaging over many periods. Okay, so for the practice, so for intensity measuring instruments, Stokes parameters provide the complete description of the plane of the monochromatic electromagnetic wave, or even the quasi-monochromatic electromagnetic waves. So the only difference between quasi and perfectly monochromatic is that the monochromaticity or the coherence is lost on a time scale of order delta t. So your measurements have to be done on a time scale which is shorter than this wave packet time scale. Okay, so what else can we say? We can see the following actually. So there is something called Schwarz inequality, which says, this applies for complex numbers. What it says is that E1, E2, E1, E1 star times E2, E2 star. So basically absolute value of E1 squared times absolute value of E2 square is greater than or equal to E1 E2 star plus E2 E1 star. Right, it's actually not that hard to see. So if, for example, E1 goes like A1 e to the I phi 1, okay, and similarly E2 has the same form. So this is nothing but A1. A1 is a real number now. A1 squared, A2 squared, right? Now this is what? This is A1, A2, e to the I phi1 minus phi2. And similarly, this one be a1, a2, a1, a2, e to the I, phi2 minus. Right, so if phi1 minus phi2 is constant, or so basically what does this become then? So this will become so a1, a2. Suppose a1, a2 is not time variable, only phases have time variation. So this is e to the I delta plus e to the minus I delta. Right.
Sir,
So
left hand side is addition or multiplication? Should be addition, no?
No. Sorry, this is also multiplication. I'm sorry, yeah. Both sides are multiplications. Right, so basically what I'm getting at is, let me tell you. So what I want to do is I want to check the status of this equation. Right, if you recall, right, so I will actually need it for this. If you recall, for monochromatic, right, for monochromatic light, this was correct. I square equals q square plus u square plus v square. Right, but here when I do these squares, I will have like I square will be E1 absolute value square the whole square. So this is actually not, yeah, this is product. Sorry, my bad. Yeah. Sorry. I was really making a big mistake. So this would be, oh, there is a little lag. Okay. So this will be A1 squared, A2 squared. So let's assume A1, A2 be time independent, but phi1, phi2 to have time dependence. So this is e to the I delta phi and e to the minus I delta phi. Now, if delta phi is constant in time, right, then they are just complex conjugates and they multiply and give you 1, right? But if delta phi is dependent on time over a time scale for this averaging, then this will not multiply and give you 1. It will give you something which is less than 1. So that's why this is greater than or equal to this. Okay. So if delta phi t right, if delta phi is independent of time, if it is delta phi naught, then this will just multiply and give you 1, but otherwise it will not. So basically this is Schwarz inequality. What it says is that this equality will hold if E1 and E2 have a constant relative phase. So equality holds for constant or time independent relative phase. Right, this is what I actually just said mathematically here. In that case, you'll have this equality, and what you will have is similar equations. So let's actually just schematically look at I squared. What would be I squared? I squared would be E1 absolute value squared plus E2 this whole squared. Right, so this is I squared. Similarly, Q squared is equal to, how should I write it? Right. E1 squared minus E2, the whole squared. Okay. Okay, let me create a little space. Okay. Okay. So this is Q squared. U squared is equal to, this is where E1, E2 star squared plus E2, E1 star squared. Sorry, U squared is, sorry, what am I doing? This whole square. The whole square. So this will give you so this will give you E1, E2 squared and so this is this times this, this times this, this times this, and this times that. So okay, so this is what you will get, and similarly B squared and so on. Now, using this Schwarz inequality, you can actually show that for a general non-monochromatic, quasi-monochromatic light, E squared is actually greater than or equal to Q squared plus U squared plus V squared. So the equality holds only for perfectly monochromatic waves, and in general you have this inequality. Right, so how do you, basically what you have to do is here you have to write E1 absolute value square as E1, E1 star, E2 absolute value square as E2, E2 star, and then you just have to like use this inequality at some places, because you can actually see terms like E1, E2 star, E2, E1 stars appearing here, right? So these are smaller than the equivalent E1 absolute value square, E2 absolute value square. So that's how you prove this. Okay, so I'm actually not going to do this. Perhaps I can give it as a homework problem. That would be nice. Okay. Just a second. So, so this is about general non-monochromatic wave. Now, if you have a completely unpolarized light, then what happens in that case? So what happens in an unpolarized light. For an unpolarized light, the phase is actually changing randomly, right? So what does that mean? And the amplitude in any two, so phase between two components, varies randomly, right? So this is the first condition, and amplitudes epsilon1 and epsilon2 are equal. Basically what it means is that if you take any two axes, the power along the x and y directions are equal, right? And the phases are changing randomly. What does it mean for I, Q, U, and V? If you look at these, what it means is that epsilon1 and epsilon2 are equal in magnitude. So Q becomes 0, right? And phi1 and phi2 do not, phi1 minus phi2 is a random number. So if you have cos of a random number which is changing very, very fast, this averages to 0. Similarly, sine of a random phase averages to 0. So for a completely unpolarized light, you have Q equals U equals V is equal to 0. A completely unpolarized light is not at all quasi-monochromatic. It's an opposite. It's opposite of monochromatic. Monochromatic light maintains its phase, whereas a non-monochromatic light or an unpolarized light does not maintain phase relation between any two components. Is this clear? Why Q, U, and V is 0 are 0 for unpolarized radiation? Because these phi1, phi2 become like random numbers, and epsilon1 and epsilon2 are equal. So that's how, in fact, right. So Q square plus U square plus V square is 0, but I square is not 0 because, there is still power in the radiation. Okay, so that's why phase is so important, right? Okay. So I have a little bit more to do. Right. So a little bit more about Stokes parameters. So, right. So linear superposition is allowed for electromagnetic waves, right? Suppose you have independent waves, right? No, suppose you have waves which are varying at omega and 2 omega, and waves which have random phases relative to each other. So if you have Stokes parameters for independent waves, right? So these are independent waves which are linearly superposed. So independent waves meaning their omegas and phases are independent of each other. So your electric field, for example, in some direction is equal to summation over k E1k. So E1 is like the component along the x-axis, and k is like these k independent waves which are superposed to give you E1. Similarly, E2, the component along the y direction is k E2k. Okay. So Ei, Ej, if you recall our Stokes parameters, we had expressions like this, right? We had things like this. Only these things were appearing there. So if we have like E1, which is, so what would an expression like this look like? It would be just this. E I k times summation over k E j k, and then you have this is the usual averaging over the fast time variation over several 2 pi by omega time periods. Now, what does this give? This gives you this gives you summation over in fact we should just use k prime, right? So if they are independent, ek and ek prime have random phases relative to each other. Okay, so that means when you average over this fast variation, they average to 0, right? If k and k prime have random phases, since they are independent of each other, there will be no cross terms. It's sort of like that random walk, right? Ri, Rj, if two things are uncorrelated with each other, their averaging will give you 0. So what you have is E, I, K, E, J, K, and there is a star here, right? So you'll get this, and now this K is over all these independent waves. So all you have is, basically all these terms will just be a superposition of your Stokes parameter. So basically your total Stokes I will, for example, be, Stokes I involves only E1, E1 star and E2, E2 star. So all you have is all these independent I's for these K independent waves will just add up. Similarly, Q will just be adding of QKs and U's and V's too. So all Stokes parameters just get added for independent quasi-monochromatic waves. Okay, this is clear, right? It's actually simple in that way. So the superposition principle applies. So basically superposition, this is a consequence of superposition and independence. Okay, we can also do one thing. So we can actually write, so I, Q, U, V, these are the Stokes parameters. We can make a column vector of these and we can write them as I minus Q squared plus U squared plus V squared 0, 0, 0. We can write it as a linear superposition of these two, Q squared plus U squared plus V squared and Q, U, V, right? They obviously add up to give this. Can someone tell me why would we like to write it as this and this?
One part is completely unpolarized and the other is polarized.
Absolutely. So this has Q, U, and V 0. That means this is unpolarized component. Okay. And here this square is equal to this square plus this square plus this square. So this is perfectly polarized component. Okay. So an arbitrary wave is a superposition of completely polarized and unpolarized light. So in general, waves have both polarized and unpolarized components, and we express it in terms of polarization fraction. So we can actually define a degree of polarization. What is degree of polarization? This is equal to pi. This is the symbol used, is equal to intensity in polarized part divided by intensity of the light in total intensity, which includes polarized intensity and unpolarized intensity. So if you write it like this, what would that be? This is the polarized intensity and this is the total intensity. So this is just Q squared plus U squared plus V squared divided by I. So for unpolarized light, this is 0. For perfectly polarized light, this is 1. Okay. So, in fact, So, so there is an example given in the book that if you have only, so if you have polarization which is only linear polarization, right? So linear polarization means that your V is equal to 0, right? So in that Poincare sphere, you lie in the mid plane. That's what linear polarization is. So if you have a linearly, so the polarized component of the light is linearly polarized, and you have unpolarized component. If that is given, and if you have a linearly polarizing filter, right? So basically what you are given is you are given some light, and you are given this linearly polarized filter, and you are allowed to rotate this polarizer. So what you will see is, if you sort of plot I out by I in, right? If you plot I out by I in, the intensity of which comes out divided by intensity which is put in as a function of this angle of the polarizer. So this angle theta is the angle at which this polarizer is oriented, right? So when this polarizer is along the direction of this linear polarization, then this would be 1, right? So let's sort of take theta to be aligned along the direction of this linear polarization, right? And when it is transverse, the linearly polarized, so basically it will vary like this, of course, periodically for theta going from 0 to so this is 0 to 2 pi. So basically, right, so this is what, right, this is when it is not allowing any polarized light. This is when it is not allowing any polarized light. So what is Imax? What is Imax? The maximum intensity measured here is when the polarizer allows the total polarized intensity, right? And I unpolarized by half. See, always the unpolarized light, only half of it will go through the polarizer, independent of what the orientation is. The reason being, right, the unpolarized light can be thought of as any transverse polarizations which are uncorrelated with each other. So the random phase varying along the direction of the polarizer gets passed, but perpendicular to it does not pass through it. Similarly, I min is what? What is I min? Can someone tell me? When the intensity measured
Only when I polarized is 0, so we are looking at a direction where it is, I mean, it's linearly polarized, so it will not contribute. It
basically
will
this is what you have, right? Because when it is, so if you have totally unpolarized light, whatever the direction you orient the polarizer at, you will get half the incident intensity, because it's not letting other half go. So in this case, you can actually see what is pi in terms of I max and I min. Right, so this is equal to I pole plus I min. So I pole is nothing but I max minus I min. So that's the numerator of pi. And what is I? I is nothing but I. Total intensity is nothing but I pole plus I unpole. Right? And that's nothing but I max plus I min. Okay, so if you have, so this is not valid in general. This is only valid when we know beforehand that the light, the incident light here is linearly polarized. Right? In general, it can be elliptically polarized, and a combination of elliptical circular polarization. Okay. Now, if I give you that if this is LP plus CP, then actually this will not hold. In fact, it's a good idea if you try out what what the outgoing intensity will be if this is circularly polarized. Right? If this is circularly polarized, again it will just let only half go through, because circular polarization has equal power in two linear polarizations which differ by a phase of pi by 2, right? So circularly polarized light will behave like this, but for a different reason, not because the two components have independent polarization, but because it's fixed and pi by 2. Anyway, so we are done with the Stokes parameters, so I encourage you to read chapter 2 of the book and derive some of these mathematical, complex number algebra that we sort of very quickly went over. The key ideas are actually this idea of coherence, right? This idea of polarized light and unpolarized light. Unpolarized light has no coherence, no phase relationship between the two independent polarization directions. Okay, and in general, a quasi-monochromatic wave will be coherent only for a finite duration, right? If the envelope changes, if the phase of the wave changes significantly over a time scale, they become coherent. So these are important ideas. Okay, so I'm actually going to put some of these things in the homework problem, which I will post in a week or so. Again, it's sort of the idea is very similar to the previous homework problem. I'll have problems which will cover material which we have not covered yet, but we will cover by the end of this month. Okay, any questions? Okay, then I will stop recording and end the class. And I encourage you to come to the Friday tutorial, because Ankit will go over the solution and I'll also be there, and you can ask your doubts. Okay, then I will stop recording and